Chuck,
Hey,
time for things you thought you knew.
yes, and in my case, things I know I didn't know.
That's a very important state of mind, to know what you don't know. Because if you didn't know what you didn't know, that's just abject ignorance. I mean there's
That
no
is true. That second part is sad. What you just
sad,
said.
exactly.
That's sad. Ooh, that's
sad
that's
ignorance.
terrible. That's sad ignorance, man.
All right, so Chuck, how do you know how big something is?
Yeah, measure it.
You measure it, right? So you pull out a
Yeah.
ruler. Let's say it's a table, and you measure it. Okay. So there are two things working against you on that.
Mm-hmm.
One of them is, how close together are the hash lines on the ruler,
Right.
right? Because if your table ends up between two of them, then you don't know how long your table is. If you're going to report to me, you can only say it's between here and there, and venture a guess to where it is from one marker to the next.
Okay.
It's kind of like half, maybe. What you'll give me a guess, fine, but you won't know exactly because you don't have the metrics to determine that. Okay?
Right.
Now
It's like
watch.
measuring in hands. He's 7 hands tall. Really? That's all?
Well, hands is actually a specific measurement. I mean, I think the hand is 4 inches.
Oh, really?
The width of your hand. Yeah.
Look at that. I see. Now I just learned something there.
Horse heights are measured in hands.
In hands, right. I knew that the horses were measured in hands, but I didn't know that the hand had an actual unit.
It's around 4 inches. Don't quote
okay.
me on that. But
All
yeah,
right, that's
yeah,
cool.
yeah. Okay,
That's cool.
okay.
Good stuff.
Okay. So even if you had the precision to measure the length of the table, if you go down under a microscope, like a really good microscope, like an electron microscope, that's the kind of microscopes where you see all of the hairs on the bugs, and you see the eyeballs of the fly. Those kind of microscopes. If you do that, you'll see that the edge of the table is not smooth. It's actually got texture. So which feature of the texture are you going to measure it to and then report back to me the width of the table?
Well, okay.
What happens is at some point you just give up and say, Neil,
I can't.
you're
You
annoying
can't measure
me.
anything. Right.
you can't measure anything unless you
can't
just
measure anything.
agree. You just agree how you're going to take the measurement, and then you're good with that. Well, if you have that problem with solid objects, imagine the challenge measuring the extent of gaseous objects. Just imagine that. Okay.
Yes. I believe you measure that and how bad it smells.
Not all gas came out of your rear end, okay, in this world. Just saying. So you can ask, how high up does the atmosphere go? Well, so you ascend, and you say, is there a sign that says you are now leaving Earth's atmosphere? No. No. The atmosphere gets continually thinner.
Right.
And you know this because as you ascend a mountain, the air pressure drops. It's harder for you to breathe. You can still breathe, but just every lung's worth of air has less oxygen in it. Mm-hmm. Okay? That's your evidence that the air pressure is getting lower and lower and lower.
Should have never smoked, man.
Okay.
God, this is killing me.
This continues. You go into an airplane. Airplanes are pressurized.
Right.
Which means they put air in there. Otherwise, you would suffocate if you roll down the windows. All right? So those oxygen masks, those are there in case the airplane loses pressure. And you're breathing very low density air, has hardly any oxygen in it. Right. So you breathe through the mask. That's all. Okay? By the way, you could hold your breath until you did this. I mean, you're not going to die immediately. You have to fight for them. It's just air. Okay?
Right.
You've held breath holding contests for longer than the time it'll take you to reach for one of these yellow masks.
Little cups, right? And remember,
okay.
people, always put your own mask on first before you try to put the mask on that of a child. So, which, by the way, no one had to tell me. Okay. Like when I heard that, I was just like, and what else would I have done? Okay.
Chuck was first out of the box on that one.
Exactly.
Yeah.
I was like, this kid ain't bringing nothing to the table. Really? I might just let the kid pass out just so I can get some rest.
Oh, that was the noisy kid.
Right.
You're not giving him the oxygen.
Exactly. Wait, let's not be so quick there, Mom. That kid is looking real peaceful right now.
Jack,
All right.
that's cold. All right. Oh, by the way, it's also literally cold as you leave Earth's surface because you're farther away from the heat point of the heat generating point, which is, that's another, scratch that. That's
Whole nother explainer.
Whole nother. Okay. So as you ascend, the air just simply gets thinner and thinner and thinner.
Okay.
There is no spot where you say it ends here and it's space. No, there isn't. So you just have to agree on what that altitude will be. Pick a thing and then just, you good with that? I'm good with that? Fine. Put it in the books. Move on to the next problem. Okay.
Okay.
So there's a guy in the 1960s named Karman.
All right.
Okay? He was a Hungarian, I think, but worked in the United States. And he said there must be an altitude above which the atmosphere is no longer scattering sunlight above your head so that it's no longer sky blue. The blue goes away and then you just see stars in broad daylight.
Oh, wow.
That's an interesting threshold, right?
That is.
And that's fair. There'll still be air molecules there, just not enough to scatter because that's how you get a blue sky. It scatters the blue of sunlight, and now the sky is glowing and you can't see the night sky. You can't see stars in the daytime sky.
Gotcha.
So, because it's daytime. However, if you ascend high enough in the atmosphere, there's a point where there aren't many molecules above you. Bada bing, the sun is still there, but you can see stars in addition to our own star in the sky. So that's called the Karman line. And ever since the early 60s, the Karman line has been the functional definition of a transition into space, whether or not you were in Earth orbit.
Interesting.
Our first astronaut, Alan Shepard, went up in 1961. He went into suborbital, was fished out of the Atlantic, okay, and he went high enough to go above the Karman line. So that counted, and so that's sort of our astronaut threshold. Karman himself, however, knew that the atmosphere is not some rigid thing, it's gas.
Right.
And sometimes it heats up, sometimes it cools down, so it will expand, it will shrink. And so the Karman line is not itself a definite thing. But if you're going to look for it, you'd find it anywhere between 80, 85, and 100 kilometers. Okay, that would convert to 53 to 62 miles up. Somewhere in there. Okay, and so to say, did you hit this exact point or not? That's like arguing, which edge of the table are you using to give me the length of the table? Except worse because it's gas.
Right.
So, point is, the atmosphere continues out for thousands of miles.
Oh no.
Yeah, in fact,
Wow.
the International Space Station, which is 250 miles up.
Right.
How much higher than the 62-mile Karman line is? It's 4 times higher than the Karman line. The International Space Station is huge. It's like the size of a football field moving through the air. There's enough atmospheric molecules up there to hit the solar panels and the physical body to drop it to lower orbits than you had originally intended. So every now and then, the space station has to boost itself up back to its original target orbit because of the air molecules that hit it.
That's insane.
Yes. And that's 250 miles up. So there is no edge. And if you're going to ask me, what is the diameter of the sun? You could look this up in a book. You could look this up. The diameter of the sun, it'll give it to you. And you say, well, wait a minute. The sun is made of gas. So how precisely are you measuring? Did you take a ruler and do that? Not only that, you can say, in what wavelength of light did you measure the diameter of the sun? Do you know different wavelengths of light emanate from different locations within the depth of the sun? if you're like Geordi on Star Trek Next Generations, and you look at the sun in ultraviolet light, it has a different dimension from what it has if you look at it in visible light and if you look at it in infrared light. Then if you look at it in X-rays, all different dimensions. In fact, the solar corona, the thing that's glowing outside of the moon when you see a total solar eclipse, that's called the corona, which is Latin for crown, so sensibly, right? So if you looked at that with X-rays, that's the size of the sun. Forget the down on the sun's surface, gaseous surface. X-rays, the corona is ablaze with light. And you're going to say the sun is huge. So I just want to put it out there that the dimensions of things is really just something you just have to agree to in advance. And then you all agree, you put it in the book, and then you move on. So the diameter of the sun is the diameter it shows to us using yellow light, which is right in the middle of the visible spectrum. That's the number you're going to read in the book. But they don't tell you that, but I'm telling you that.
I'm glad you did, because it's good to know they've been lying to me all this time.
Oh, by the way, and you can think of other definitions of space. I got one for you. You ready? So airplanes use fuel. It's called aviation fuel. There's a word for it. I forgot what. But anyway, it uses fuel. So fuel, our common understanding of fuel is you burn it and then you get energy. But what does it mean to burn it? It means it gets attached to the oxygen molecule, creates a third other product, right? There's that molecule, the oxygen molecule. They merge and make this other molecule, and it's exothermic. Energy gets generated. Okay, that's how cars work. That's how airplanes work. But where's it getting its oxygen from? The atmosphere. Okay? Wait a minute. But if you're a rocket and you're going to where there is no oxygen, where there's not much oxygen, you got to bring your own oxidizer. You can't depend on the atmosphere. So you could say you enter space at an altitude where an airplane can't get enough oxygen to fly anymore. And it just drops out of the sky. That's an interesting threshold. You could have done it that way. Because above that, you need a rocket. And we all know rockets equal space. Okay?
There you go.
I can think of 10 other ways you might define it. But I'm just saying, just numbers and measurements of things they're not written in tablets. You have to agree on what it is you're trying to measure, write down that number, and then move on.
There you go. Measurements not written in tablets, only commandments.
All right, that's all we got time for.
All right.
Yeah, that's a crazy subject, but I have to put it out there.
No, that's very cool.
And when you hear people arguing over the Karman line, just sit back and chuckle and say, the Karman line is an idea more than is an actual place within Earth's atmosphere.
Well, if I ever get into an argument about the Karman line, my answer will be, so how big is the sun?
And also the 100-kilometer Karman line. Did you really think the atmosphere is layered into evenly divisible numbers in kilometers? Did you really think that's the case? If you look up Karman line, it's 100 kilometers. Yeah, right. The Earth is like tight with the metric people, right? It's like, no, 100 is well above whatever Karman was talking about. But if you want to round it up, you round it up to 100 kilometers, and that's the definition. Fine. Okay? And the American definition is lower than that. We're like at 85 kilometers up. We have a lower definition than Europe and the rest of the world do.
Oh, well, yeah, that's because, we want to be able to say we went to space.
We want to be able to say that Alan Shepard went into space.
Went to space.
Correct.
Exactly.
Right.
We're the first people to do it, It's,
Right.
It's just like we put a spire on top of the Freedom Tower, and it's like now the tallest building in the country.
Exactly. Yeah. All right, Chuck, we got to end it there. But if you hang on, when we return, we'll go into another segment of doing some explaining. Stuff you thought you knew. That's what this is all about when we return. So, Chuck, we're back.
Okay.
For another explainer.
All right.
This one, did we talk about this before? I have a bad memory for what I've been talking about. But I'm going to do it anyway, and if it's not, we'll just do it again. Here it is. You ready?
Okay. What is
Okay.
it?
So there's an interesting difference between being an astrophysicist and being a photographer. Okay?
Okay.
Here's the difference.
A college education? I mean, I'm trying to.
Okay, here's the difference. We know that when you have an object and you heat it and its temperature rises, it actually radiates energy. Okay? If it's very cold, it'll radiate radio waves and microwaves. In fact, the whole universe is 3 degrees absolute zero, 3 degrees above absolute zero. Very cold. At that temperature, microwaves get emitted. So the universe is a source of microwaves upon us because of that leftover temperature from the Big Bang. Heat anything more, I don't care what it is, heat it some more, and then the energy it'll start giving us will start shifting in the spectrum, and then it'll start giving us infrared energy. Okay? You can't see it, it's not glowing visibly yet, but if we have sensors that are not our eyes to detect infrared, you know what it's called?
No.
Touch. Okay, you can touch it. Okay.
Heat, right? Yeah.
Yeah,
So
yeah.
there you go.
If it's warm, you can detect low level infrared all the way up to high level infrared just by getting near it, and you can feel the energy, or you can touch it and you can feel the temperature. Okay.
Okay.
So Chuck, it gets a little warmer than infrared. Now it begins to glow red, and so now it's giving you energy. It's giving you photons in the visible part of the spectrum. Say, hey, that's hot. That's glowing red hot.
Right.
Okay. But I know that you can keep making the temperature higher. It'll still glow, but now it's going to glow white hot and then glow blue hot. And the blue hot is the hottest of the glowing temperatures. But we don't experience that in everyday life. So
Nobody says blue hot anything.
anything. They don't say that anything. Plus, ice and icebergs have this blue tone to them. So psychologically, it all feels different. But here's what's interesting, okay? When we transitioned from incandescent bulbs, the old-fashioned Edison light bulb, to LEDs, okay? Ask yourself, why would a light bulb giving you visible light ever get hot? Because it's glowing white hot, but it's also still giving off infrared. Okay? So, but wait a minute, I have a light bulb so that I can see. So the 100-watt light bulb, or whatever the wattage you bought, it turns out most of that energy is coming out in the infrared.
Yes.
It's
Which
a
is-
waste.
Which is why they would always say on the package, it would say, wait for whatever, however long before changing the light bulb. Because so many people be like the light bulb would blow out. They would go get another light bulb, come back, go to change it, and burn their hands. That's how hot the bulb was.
It's a complete waste of everybody's energy. The fact that we had light bulbs that was giving us infrared.
Wow.
So, the brilliant thing about LEDs, and let me remind you, LEDs are of this next generation interior lighting. We couldn't do it until we had all 3 colors of LEDs. We had red LEDs.
Right.
We had green LEDs. We didn't have blue.
Blue.
And that would, once we got blue, we'd have RGB. You can combine them, and RGB combined in light. Doesn't work this way in paint. Don't tell your artist friends this. You combine RGB with light, and you get white light. The thing about LEDs is they're not glowing. They're not glowing from heat.
It's actual white light.
It's actual light coming out at those frequencies, at the red frequency, at the green frequency, at the blue frequency. Your eye merges them and you see it as white light. There is no energy coming out in the infrared or anywhere else.
That's
So that's why you could have a 3-watt
Yes.
LED bulb that just kicks ass against a 60-watt, or however many, 5 watts, whatever, against a 60-watt Edison bulb, regular old-fashioned bulb, because most of that Edison energy is coming out in infrared, and none of that energy is coming out in infrared for the LED. It's all in the visible part of the spectrum.
I don't know why we didn't do this one so much earlier, because 2 things. And it's so exciting that you just actually did everything you just did and related it to light bulbs. 1, people went crazy when we said we were going to transition to all LED light bulbs, and they did it because President Blackula said that we should actually move to all LED light bulbs. And people were like, now the government's trying to tell you what kind of light bulb you can have. No, I swear to God, it's my God-given right to have me a regular incandescent light bulb. That's America. And so people lost their minds.
What's Chuck's imitation of America?
They lost their minds.
They lost their minds.
And what you are saying is, 1, it's more efficient because it is exactly what it is, which is
so it's energy efficient by a factor of 10. Okay.
Right? And then the other thing you said was that is why you see on the box it's whatever many watts instead of like your 200-watt bulb or whatever. It's like, it says they do lumens now.
Yeah, you can't use watts because you know what watts are. Watts is not the measure of the brightness of anything.
Right.
Watts is the measure of how much energy, the rate at which it's consuming energy.
Exactly.
And since we all had the same light bulbs, you could compare watts and say that one is, twice whatever. You had some sense of that.
Right.
But really with light bulbs, it should have always been measured in lumens. In fact, in Europe, I think they always measured it in lumens. Yeah. So you're after lumens here. You're not after wattage. Okay? So this is a maturity of the American population.
Yeah, this is the best reason for you people to go out and get LED lights. I mean, for me, I got into this because it's great for the environment. If we all did it, we would really lessen our carbon footprint for the entire nation. But the fact is, here's why you should do it. You save money. You just proved how much more efficient it is. You
save your own damn money.
Save your
Correct.
own damn
Even if you don't care about the environment, care about your own damn wallet.
There you go.
So, and that's why you can go up to any LED bulb and it's not hot. It'll never be hot. It's not about being hot.
Man, that's great.
And here these people say, Earth is flat and I don't like science and the person who discovered the blue LED got a Nobel Prize for that because the moment that got discovered, it blew open the entire lighting industry. Because now you can make white light. In fact, you can make any color light. That's why you can get LED controllers where the light itself has an RGB diodes in them, and you can just control the ratios of those and get any color you want. Mm-hmm. And so you can the Empire State Building is lit by these things, okay? And it's the intensity of the color is very real and it's very in the moment. So just thought I'd tell you that.
That's super cool. Well, listen. White light was what we were striving for, but always remember, only black light can make your dorm room look cool.
Oh, by the way, so black light, just to be clear, is an ultraviolet light. But the part of it you see is the violet that's just kicking into the red, orange, yellow, green, blue, violet part of the spectrum. You can see that, but that's not why you have it in your dorm room. You have it because the ultraviolet light interacts with the pigment in the pictures on your wall, the posters, and it forces the pigment to glow. Okay? And it's called phosphorescence, right? And so that high energy light that you can't see, the pigment can't see, it absorbs it, and then gives it back to you in visible light, and it looks like the paintings are glowing. So in a sense, it is black light. It is light that you can't see.
Nice.
Yeah.
All right. Well, this was great.
You got it, Chuck. So next time you walk by an LED, just pause and say, "Thank you, science."
There you go. Just say that anyway.
Say that anyway.
Just say that anyway.
Wake up in the morning, take a deep breath. Thank you,
Thank you,
science.
science.
I should tweet that. I'm going to do that. Let me see if I
Exactly.
can start a movement. So, Chuck, that's the end of this segment. When we come back, we're going to do another one of these, Chuck.
All right. Sounds
Okay,
good.
you got it in you to listen?
I got
to
it in me. Let's
hear
do
out?
it.
Okay, all right. We'll be right back. Jet,
Hey, Neil.
I'm back with another sort of stuff you thought you knew.
Right on.
This one might be something you didn't even know you didn't know. How about
Okay.
that? Some of those are out there too, right? So no one told me this. I discovered this on my own. That if for those of you who have ridden airplanes, I know some people have never been in an airplane. I highly recommend it. It's quite a marvel of engineering and physics and aerodynamics.
Or you can watch YouTube.
Okay. Okay. So if you could save up, if you've never been on an airplane, find a place to fly to and just check it out. It's quite a marvel. And I marvel at it every day, even though we've been doing it for more than 100 years. So I noticed when I pull down the shades, and I can't see outside, and I look at this drink, and the water level is completely horizontal.
Okay.
All right, that means we're just there. We're not, accelerating or banking or turning. Okay, it's just there. And it stays that way the entire trip.
Right.
Now, I know the plane has got to make some turns when it comes near. I know it's got to do this at some point.
Right. Yes.
If it does that, I would expect the water level to tilt within the glass. I'd expect me to lean in one way or another, the way it would happen in a car. If you make a left turn in a car, your body leans to the right, okay? Because you actually want to keep going in a straight line, but the car is curving in front of you. So it feels like you're getting pushed to the right, but really you're just going you want to go in a straight line. The car won't let you. And you're getting pushed against the door. Okay, or you turn left or right, whichever, or someone's sitting next to you, your shoulders will touch. All right, no longer does that happen on an airplane. So what I did was, let me try this with the shade up. I do it with the shade up. I look out this window, I see sky. I look out across the plane, I see the ground. This sucker is banking, and yet the water on my table is completely flat.
Okay.
So, there's only one thing that can be happening here, because I don't think humans have this ability. The computer is flying the airplane, and you program into the computer such that the radius of the turn and the speed at which you're going requires that the plane be at a certain banking angle so that all the centrifugal forces combine with gravity so that you don't even know you're banking this turn. In other words, the urge to fall into the middle of the circle gets completely balanced with the centrifugal force to send you out of the circle so that the gravity vector still goes directly to the bottom of the glass and to your rump into the chair. And you don't even know the plane is turning. Those three numbers, if you choose them correctly, you can have them conspire so that you would never know the plane was ever turning at any time.
Well, clearly you have never been on Spirit Airlines.
Top the pilot's in there.
They don't even use the joystick. They use an actual steering wheel.
I'm sure it's a fine airline where they have fully trained pilots. But the precision necessary to do that reliably, to do that without the judgment of the pilot, is that takes a computer. And if you look at old movies where they show people on airplanes and the airplane is turning, you'll see people sort of leaning to the one side or the other. Right. That is no longer a thing in airplanes.
And you know what you just reminded me of when you're talking about going back is old episodes of Star Trek, the first Star Trek, where the entire crew would go to the left, and then they go to the
They
right.
leaned. Hold on. And they'd all be instructed to do this, right?
Right.
So they take the camera and tip the camera,
And
right?
they tipped the camera, and they would all do that to make it look like they were banking, and they were in space. So
So if you bank a turn properly, you never feel that effect. And by the way, we've talked about this with NASCAR. All right, what the banked turn in a racetrack, there is a speed with which you can drive your car so that you never have to touch the steering wheel, and the car will make a complete turn on that bank and end up going back the other way.
right.
And that speed is one where you will not feel like you're leaning to the left or the right.
Because the road is turning for you.
The road is turning the car for you. Correct. And at the right speed, you'll feel the gravity vector doing whatever it was doing before you entered that turn. It's the same physics principle at work there. So I just thought I'd put that out there. Just a little discovery I made. I haven't checked with anybody who did it and when it started, but I began noticing it. And you should notice it too. Just check it out. There could be sky here and ground down there, and you don't even notice it unless you look out the damn window.
Yeah.
Just saying.
Well, I fly Spirit, so I notice it all the time.
It's tough. Wait, one last thing. If you are in space, there is no banking of turns.
Yes.
Okay.
Right.
Well, I'll tell you why. Because so on a track, the thing that's turning the car for you is the road itself.
Okay.
Okay. That's a force there that's turning the car. If you are in an airplane, you are banking on a cushion of air as you complete your turn. If you're in space, there is no force doing that. So if you're in space, you just have to fire rockets.
Right.
And so they don't tip and turn. It looks cool when the TIE fighters did that in Star Wars and
Right.
and the Millennium Falcon. You know, it looks cool, but that's not how it would happen. You just have the rockets change the direction that it turns in.
So all of those maneuvers that you see the Millennium Falcon make when in
Yeah, the
space,
maneuvers they're atmospheric maneuvers. They're not vacuum.
none of that
maneuvers.
means anything.
Right.
It's
right.
yeah. Wow.
Plus, didn't they at the end of the Star Wars Episode 4 when they had when they were celebrated for destroying
The Death Star.
the Death Star, didn't they just fly in from an open bay exposed to the vacuum of space, and then they just get out and walk around?
Yes.
I see.
But I think there's a force shield that holds the atmosphere inside the ship, though.
You just made that up right now.
No, I'm serious. That's
Okay.
Yeah, no, I'm
Okay.
serious. I think that's how it works. There's a
Okay,
force
magic
shield that
force
holds-
fields. Okay,
Yes,
fine.
I mean, but seriously, there's nothing in Star Wars that's scientific. Let's be honest. I mean, seriously, there's
You know, the
absolute-
least believable thing to me was here are the fighters coming in, and there's the guy with the traffic cones directing.
Yes,
it's
they
like
still right.
you don't have a better way to do this in
Yeah.
the 25th century or whenever the hell this thing takes place.
And the other thing is too, they all fly in, and nobody fires retro rockets.
Oh, they just slow down.
They just
yeah.
slow down. Like in
Yeah,
Star Trek, though, when you fly into a shuttle bay, there is a kind of like a tractor beam that grabs you, and then you come in, and that's how
Yeah,
you
correct,
stop.
correct.
But
Because Star
in-
Trek thinks about science.
Yeah, but Star Wars, they're just like, coming in. I'm coming in hot.
All right, so this is Airplane Banking 101, Chuck.
Well, that's cool, actually.
All right, this has been an explainer jamboree. Stuff you thought you knew in 3 segments. And so I hope you like these, Chuck, because I bend your ear on them.
I love them. They're great. I mean, and I actually do learn stuff. And I got to tell you, man, it's great information to have at a cocktail party.
Okay. Because you'd otherwise just be completely boring at a
Exactly.
I got to pull out a nihilism here. Just
Exactly. It's like, you should go talk to that guy. I thought he was a stupid comedian, but God, he's brilliant. Guy is brilliant.
All thought he was a stupid comedian. What kind of stuff? So, Chuck, we got to call it quits there. But this has been fun. I'm glad to teach you a couple of things.
Yeah.
I'm an educator, and I feel like I have purpose in life, and that I'm somehow fulfilling that purpose if I get you to learn something. Because you're a smart guy, and you know a lot. Well, so it's a challenge for me to find things that you might not know, really. I'm just letting you know that.
Well, there you go. That's I don't think it's much of a challenge, but I'll accept that as a compliment.
So another stuff you thought you knew on Star Talk. This is Neil deGrasse Tyson, as always. Keep it cool. Hey, Einstein fans, you're about to watch a special edition Star Talk just for you, all about Einstein. Now, this is Star Talk. I'm your host, Neil deGrasse Tyson, your personal astrophysicist. I got Chuck Nice, co-host.
Sir.
I got Jan Levin, old-time friend, colleague, physicist, expert on the universe in all ways that matter, especially for this conversation because we're celebrating the life and times of Albert Einstein. So Albert Einstein was born in Germany on March 14th, 1879. And Chuck, you know what day that is?
1879, March 14th.
March 14th. Any year.
In any year.
Yeah, what day of the year is March 14th?
I believe it's the day that precedes the Ides of March. But what is March 14th? I really don't know.
Before the Ides of March, that's Pi Day.
Oh my God!
Yes.
Okay, I didn't know it was actually March 14th, but of course that makes sense. 314.
314. Yeah, you got Pi to March 14th. When written in sort of the American way, where we put the month before the day of the month.
Right.
Yeah. I mean, exactly. So 3.14. That's Pi Day. Then you get really geeky, and then at 1:59, right? 3.1415, 1:59 and 26 seconds.
Right.
And you get a full up pi moment.
Can I just suggest that that's probably the access code to every physics department in the world?
It's pretty funny. That's the 1, 2, 3, 4 of physics departments.
If you walk up to a sealed theoretical physics department, try 3.1415.
And you'll get it. Yeah. Oh my God, it worked.
And tomorrow, the missiles got launched, all because of Jana.
Yeah, I shouldn't reveal these things.
So let's talk about this. So, Jana, what is the annus mirabilis, and why do we even say that in Latin? Why couldn't we just say it in English? His miracle year.
Well, I don't know. Why do we say it in Latin? That's a different question. We'll just talk about the miracle year first.
It's America, Jack.
Because so 1905.
Yeah, 1905.
1905.
How old is he?
25.
Yeah, 20. Yeah.
So Einstein was a clerk in a patent office, and he couldn't get a job in a physics department. His father was desperately writing to famous theoretical physicists saying, my son's really committed, and
like any dad.
He couldn't get hired.
Yeah.
One of his professors called him a lazy dog, and here he is in this patent office in Bern, Switzerland, and he has a drawer at his desk that he calls the physics department. And in this drawer, he has these scientific papers he's working on in between finessing other people's patents to make them better.
Wow.
And in that year, he has this extraordinary year where he publishes a series of 3 papers that absolutely transform modern physics. One of them is on the special theory of relativity. One of them is on Brownian motion, which refers to the atomic aspect of air and molecules. Like if you see a little piece of lint, you notice that it takes a zigzaggy pattern, and that's because it's all these little atoms
hanging on it.
And the photoelectric effect, which is staggering because it probes the wave-particle duality of light, that sometimes light acts like a wave and sometimes it acts like a particle.
Did this by the time he was 26.
Yeah.
Chuck, how old are you?
And unemployed.
Verify.
I'm 22.
Okay. There's still time.
I got time.
Okay, you got time. Thank you for verifying that. So we call it an annus mirabilis.
Why do we say it in Latin? Because it was all in German?
Did that get him a job?
Oh, yeah. Well, he did become to the credit of the scientific community, even though this outsider was publishing these papers, it was very swiftly accepted, the significance of all of these papers, very swiftly. And that should also be a lesson to those many people who send me their theories, that when they're transparently correct, they are grabbed at with glee.
Right.
And,
all the most amazing, mind-blowing, earth-shaking scientific research was published in legitimate journals, accepted by peers.
Yes.
By peer-reviewed. So as they say, to be a genius is to be misunderstood.
Right.
But to be misunderstood is not to be a genius.
Oh, that's nice.
Yeah, that makes sense.
So you can't come to me and say, I have an idea, but the establishment is not, they're going to reject it.
Therefore, it's brilliant.
Therefore, right.
They don't get this, man. They just don't understand.
Right.
I'm starting a Facebook page for everyone to evaluate, so they don't have to come to us.
I'll tell you right.
They just, amongst themselves, talk amongst yourselves.
Talk amongst yourself.
Yeah, well, now we have Twitter for that. You know what I mean? It's,
Now, he didn't call it special theory of relativity. So who called it special?
That's interesting. I actually don't know specifically the history. I mean,
Why do we have you on the show?
Because I could explain
Someone
relativity.
out there know why?
I mean, the general theory obviously came later when he included the curvature of space-time, but I don't know who actually coined it special. It was just the theory of relativity at the time.
Because the paper was on the electrodynamics of moving bodies. That's the name of that paper.
Yeah.
Of the special relativity paper.
Grabbing title. But the
Page
amazing
turner.
thing,
So that was, 1905.
Yeah.
And then a general theory comes out when?
1915.
So that's 10 years.
Yeah.
And he basically pulled that out of the ether.
It's probably published in 1916, but it's like it's 10 or 11 years of struggling with the mathematics to elevate what we now call the special theory to the general theory.
Working alone.
Yeah, I mean, he was being influenced by people like Grossman, who was a mathematician. Hilbert was very influential. So Einstein wrote down several wrong theories along the way. And there's actually a kind of adorable story when he was thinking about something like gravitational waves, where he kept changing his mind in print. He would write papers, say they're
Adorable
real.
for a physics story.
yeah, well,
Was it?
The record.
adorable for a physics story.
Let the record catch that. Pause for a moment.
Right.
Yeah.
And right after this, believe me, we're going to get to some very darling theories.
So
Cheeks you just want to pinch. Yeah. All right, go
he
on.
writes a paper saying gravitational waves are not real. Then he writes a paper saying they are. Then he writes another paper several years later saying that they're not. In between acceptance of this paper and publication, he sneaks in a draft of a manuscript that says that they are. And one of his colleagues says, Einstein, you have to be really careful. Your famous name is going to be on these papers. And he just laughs. He says, my name is on plenty of wrong papers. You do not need to worry about that. So it takes him a long time. I mean, there's decades of him figuring out gravitational waves. And the general theory was 11 years, and he needed help from other people. He wrote down several
idiot.
wrong theories.
No.
What a deadbeat.
Einstein, you dumbass.
10 years.
Is that actually is that actually something that is? Did that do anything
In
to?
retrospect, that is short order.
Right.
Look at string theory. We're decades deep.
They're still in it for decades
Yeah,
after
it might
decades
be
after
it might be hundreds of years. I mean, there's no
decades. And that's
human scale
dozens of leaders in the field.
really brilliant people.
And we have one guy, Einstein,
By himself.
basically. Yeah. No, I mean, I didn't mean to take away Jana's point that there are others trying to push things
Right,
along.
they're nudging him along.
Yeah.
Right.
They're nudging him along because he's actually putting something out there to be nudged.
Yeah.
Right? Yeah.
I mean, it was
good point,
really
good
interesting. It was really interesting that it was really him on the. I mean, largely there were other physicists, but him largely on the physics side and the mathematicians pulling him up because he was not actually the most sophisticated mathematical thinker. Another one of my Einstein quotes is, he says, you think you have a lot of difficulty with mathematics? You should see my difficulties with mathematics. So he was a very intuitive thinker. And he really originally rejected the idea that you had to do all of this differential calculus and this really elaborate mathematics. He thought that's ridiculous. It's totally overkill.
Pure thought
You could
should
just
be able to
think it through and it'll be like algebra. And he did that with the special theory. It was stunning, but he could not do that with the general theory. Wow. He had to step it up to be differential calculus on curved manifolds. No mean feat.
Wow.
Yeah, but it's pretty.
Yes.
Look, how did you do in
It's not
differential
only
calculus?
adorable,
say,
it's pretty.
What grade did you get in that
Yeah,
class?
I was going to say that what I kind of go with is that you don't need that.
I know. You say, I will never
I
need
will
that
never
in my
need
life.
that in my life. Like I actually use that.
So, all right. So he does this. And then in 1921, he wins the Nobel Prize but he did so many things. What did he win it for?
Well, he didn't win it for relativity,
Well, that ain't right.
which is really interesting.
That's pretty crazy.
Yeah, was it the photoelectric effect? I think technically it was the photoelectric effect. Or contributions to quantum. I don't remember the phrasing. Do you have the phrasing?
No.
It was something
I
like
might do my notes here.
contributions to quantum. Like often they're phrased in a way that
They give
removes
you
it from a
latitude.
specific, right. But it was not for relativity. And that is clearly his greatest accomplishment.
Wow, so it's kind of like if when an actor never wins an Oscar and then they're just like, all right, so we're just going to give you a lifetime achievement.
Well, he won it in 21, which is quite early in a
yeah.
way. I mean, it was pretty soon after he proposed. It's not staggeringly late after he proposed this sort of revolution of quantum thinking. And the interesting thing is that he never really accepted quantum mechanics, right? So he initiates this revolution.
What is up with Einstein?
Insulting Einstein.
Wait a minute. Is that his brilliance? The fact that he was so self-contradicting? Like he just, no, I can't. It couldn't be.
I think his
It just couldn't be
brilliance
that.
is. I think there's something to that, which is his refusal to accept something he didn't actually understand.
That's a good point.
Okay.
Plus, there was it was hard to. You got to remember the era he came from the 19th century into the 20th century. This was the towering achievement of classical physics, where the universe was deterministic. If you tell me where to stand and I measure the motions and momentum, I will predict all future of this universe. That was a certain posture that the community of physicists has. Up comes quantum physics, where is it a wave? Is it a particle? Is that some percent of the time? And and who and what was his famous quote? He was trying to tell God what to do. What was it?
God doesn't play dice. Was that the
Oh yeah,
one?
God doesn't play.
dice.
I'm telling God not to throw dice.
Right.
Oh, he tells God not to throw
I
dice?
think so. He said, no, God doesn't. I think that's quoted by Niels Bohr or somebody.
Right.
God doesn't play dice with the universe.
No, he
I think
plays
at one-
roulette instead.
Roulette. He plays craps.
Plays craps, you know.
Well, then what does Stephen Hawking say later? God not only plays dice, but he sometimes throws the die where you can't see them.
Yeah, there you go. There you go. So,
Sounds to me like God's a grifter.
and then Einstein said something else at another point about God, and then Niels Bohr, I think it was Niels Bohr, said, Einstein, stop telling God what to do. He just got pissed off. So let me tell you if you agree with this, Jana.
Okay.
So this is my measure of why I think general relativity is a crowning achievement of the human mind, greater than almost anything else. Special relativity from 1905. I think there were enough people on the tail of that, on the trail of that if Einstein were not around, special relativity would have been figured out within a few years of that date, maybe by 1910. Whereas general relativity is so different from how anybody was thinking, it might have gone another 50 years. And so this, for me, makes general relativity a greater singular achievement than special.
Wow.
I do think that you're right. It would have been many decades before it was discovered, if it had not been discovered by Einstein, general relativity. And
That's how I
that
know
is
you badass
intriguing.
among your
I
colleagues.
also think it would have looked totally different. So Einstein gave us all of this. The general theory of relativity is a theory of curved space-time, and we follow the natural curves in space, and all of this elegance of geometry. Yeah. But none of it is necessary. There's a whole bunch of extra degrees of freedom in thinking about geometry that are not at all required. And I think what would have happened is that somebody like Richard Feynman, who was a particle physicist who was thinking about interactions of particles, would have discovered general relativity, but would never have hung all of the space-time language on it.
Right.
It would have just been masses,
would have had a different
gravitons.
Facade.
Yeah, it would have looked
Machinery
totally different
And a completely different frame of reference.
machinery.
Right.
Yeah,
Everything would have been.
Yeah.
Wow, that's incredible.
Yeah, I really think it would have been like, oh, particles exchange light, and that's electromagnetism. This would have been particles exchange gravitons, and that's the theory of gravity.
Gotcha. Yeah. So was Einstein more of a poetic thinker when it came to these things? I mean, where do you get this kind of expanse and elegance that you can attach to what you're talking about?
I mean, I don't want to presume to know, but you do have a sense that here is a very visual thinker and very intuitive. And so all the space-time machinery, there might be excesses to it that are not formally required, but create such powerful imagery and tools that in that particular example, which is often rare, it's kind of the contrary of Occam's razor, where the extra machinery actually leads to better, clearer intuition than the total leanest abstraction of just particles exchanging gravitons.
That's beautiful, right there.
You should write a book or something.
Yeah. Book in there somewhere, isn't there?
Somewhere, man.
So, Jana, your book, The Black Hole Blues, it explored LIGO, just the quest, not so much LIGO, but the quest to measure gravity waves.
Yeah.
And what effort that would take. So, how could you describe to me what's going on when two black holes collide, and how they're going to give us a gravity wave? Why don't they give us gravity waves all the time?
Yeah. So, in principle, they do give us gravity waves.
Are we giving off gravity waves now?
Yeah, right now, Chuck and I.
Okay, right. You
It's just pretty modest.
Right.
So if you think about how weak gravity is, like the entire Earth is pulling on me, and with my little arms, I can resist.
You can lift stuff away from
whereas
the Earth.
if it was charged, if there was that much charge pulling on me, I'd be liquefied. So gravity is incredibly weak. It takes an entire planet to even make it hard for me to walk.
That's a good thing, then.
There's another quick calculation you can do. Back when we had a space shuttle that would launch people into space, if you took all the electrons out of 1 cubic centimeter of the nose cone, just remove the electrons and put them at the base of the launch pad,
That would be
the
it.
shuttle wouldn't be able to launch.
Wait a minute.
Because the electrons would
Just
be
the electrons.
in 1 cubic centimeter.
1 cubic
At the
centimeter.
base of the launch pad.
Right.
They would be pulling on the leftover extra protons that are at the top. They would be attracting one another.
Right.
You would not be able to launch this.
Right. You could. Oh,
Right.
wow.
So the
1 cubic
difference-
centimeter.
1 cubic centimeter.
Right.
So the difference between the gravitational attraction between like an electron and a positron and their electromagnetic attraction is something like a trillions. So it's that much stronger, the electrical attraction,
Wow.
than the gravitational
And gravity.
attraction.
It's the gravitational pull.
It's weak.
It's like
So gravitational waves are incredibly weak, but so what you need in order to have any aspiration, even Einstein didn't think this would be possible because he didn't think anything in the universe could possibly bring space-time
pre-black
loud
hole.
enough. It's pre-black hole. So you need something like the tremendous radical concentration of mass and energy in a black hole. You need them, not only that, but you need them to be in the final throes of their orbits together. So it's like mallets on a drum. When they get closer and closer, they're getting louder and louder. And it's like this crescendo. So when LIGO made its first detection, it was the last 1/5 of a second of the orbits of two black holes, each one about 30 times the mass of the sun, a couple hundred kilometers across. They're going very nearly the speed of light, and they're executing, a few orbits in the final 1/5 of a second, and
then
boom, it's finally loud enough that even though it's traveling for 1.3 billion years across the cosmos, by the time it hits the Earth, if you think about the time it left, that just multi-celled organisms were differentiating on the Earth.
Yes, they were.
And there's this race, they're building LIGO, in the final 100 years, and then boom, when it hits, it's just barely loud
and
enough.
all the while that wave is heading towards Earth.
That's right. But it could have been for the previous several billion years it's been ringing the Earth, but there was nothing there
Right.
capable of detecting it.
Yeah. Now, is there any way that we could have missed it?
Yeah, many ways. So that actual night that the first detection was made was supposed to be the first science run of the advanced instruments. It was in September 2015. And they decided they weren't ready yet. So they canceled the science run. Wow. And instead they were there. It's like Sunday night, Monday morning, in the middle of the night, hammering on the instrument, trying to mess with it just as tests. They're literally driving trucks along the access road, slamming on the brakes to see if it screws with the instrument. And then in the middle of the night, they get exhausted. They put their tools down, they go home. The same thing happens in Washington State. This is in Louisiana. And within the span of an hour, this thing that's been traveling 1.3 billion years smacks the instrument.
Doesn't that tell you that this is happening more frequently than we think?
Way more frequently, because everyone told me, with the exception of Kip Thorne, that black holes would be years on, that we would detect all kinds of things first that we predict existed, but black holes were far off in our future, and they were not only the first things we detected, and it was beautiful black hole signature, but it was the first 4 things we detected were all black hole collisions.
Oh, look at that.
Black holes all the time.
All black holes all the time.
Exactly.
So what's the future of this?
Well, a wonderful thing happened not too long ago. They made an announcement that they detected the first neutron stars colliding. So neutron stars are dead stars that aren't quite big enough to become black holes. They're under 2 times the mass of the sun, and they're dense dead stars. They're often highly magnetized. But the interesting thing, see, black holes are empty. They're just darkness, empty space. There's nothing there. So when they collide, it's in darkness. The black hole
Just
collision.
to be clear, when we say that a black hole has a certain size,
Yes.
that's not a physically
Right.
occupied volume.
Exactly.
Describe the size of a black hole.
The size of a black hole is really just the extent of the shadow that it casts on the sky.
By convention. That's
Yes,
what we,
by convention. It's the region beyond which light cannot escape. And so it is literally just the shadow cast on the sky. If you were to,
three-dimensional shadow.
yeah, if you
That
were
cool?
to, yeah, it's really cool.
Okay, yeah.
Did you know you can have a three-dimensional shadow?
Yeah, it's like, but you should call it black ball, not black hole.
Oh, yeah.
Well, what could go wrong? The French already objected to black hole.
Did they?
Yeah. Trou noir. It's offensive in French, apparently.
Oh,
What do they call it?
A black hole. They gave in, you know.
They gave in, yeah.
Couldn't resist forever.
Yeah. So that's the fascinating thing about a hole. When we think of a hole, we think of a circle in a horizontal surface that you go through
Right.
in a plane.
Right.
Whereas this is a hole in three-dimensional space.
Right.
You can fall into
shadow.
from any direction.
direction.
Yep.
woo!
And walking into the shadow should be as harmless as walking into the shadow of a tree. Nothing's there. You wouldn't notice anything. You'd cross right over. There's no dense material there. There's just nothing there. So when black holes collide, it's truly a dark event, which even though the first collision was the most powerful event ever detected since the Big Bang,
Okay.
none of it came out as light. None of it.
So can I ask you this?
If it did, it would be the brightest thing in the night and
It
daytime
would have
sky.
outshone all the stars in the observable universe combined.
Okay, what if we don't see what's colliding? Okay, what is colliding?
Space-time itself.
Oh.
So the black holes blob together, and the
Hold on
shadow
for a second.
distorts.
Wait, just hold on. My head.
A bout of existential
Oh God! Space
angst.
time itself.
Colliding. Yes.
Then, like this blobby thing, it sheds off all its imperfections and it settles down to be one bigger black hole. So there's a black hole out there, as far as we know, about a little bigger than 60 times the mass of the sun, that's just wandering the cosmos aimlessly, completely dark and completely quiet. But the
I'm just a
fantastic
hole.
thing is they settle down.
Yes, I'm only a hole.
Don't get in my way.
So that's amazing.
Yeah, you see it you hear it in the recording that LIGO makes. You hear it ring down. You hear it settle down to a final black hole.
So tell me how 1.3 billion light years away, we can know it's two black holes, one 28 times the mass of the sun, one 36. What is getting modeled there?
Yeah.
Give us that confidence.
There's an old-fashioned mathematical problem, can you hear the shape of a drum? And it's very similar. If I bang a drum,
That's
I
beautiful.
think that'll be the title of my memoirs.
Can you hear the shape
Nice.
of a drum?
Can you hear the shape of the drum?
we all recognize sounds. Our phones go off and we're like, that's my ringtone. So it's kind of similar. We have a prediction for how the mallets, the black holes, bang on the drum of space-time, creating a sound. And it's a very specific prediction. It's not a whole range of possibilities. We can literally hear, if I played for you our predictions, the difference between black holes that were extremely disparate in size, it sounds different. If the black holes are on wildly eccentric orbits, it sounds different. So you can reconstruct the motion, size, behavior, spins, of
With high
the
confidence.
mallets,
Wow.
with some things less confidence than others. So, like the spin of the black holes is hard to determine. They're both probably spinning. Some things with less confidence, but that there were two black holes with a pretty good degree of confidence. Yeah.
And with the masses that they were ascribed.
Right, with the masses they were ascribed. So you can tell how big they are too, because if you can hear the orbits, again, just like how you can hear mallets on a drum, and even
That's a
going-
weaker signal, though.
Well, it is, but it's 0.7 times the speed of light, and you can tell when it's done one full orbit, and that tells you how big the system is.
Okay.
And that means you've got, these two black holes summing to a little more than 60 times the mass of the sun in a region only a couple hundred kilometers across.
All right.
So how are you going to do that?
Yeah, there's only one way.
Yeah.
Right.
So are there any black holes tiny enough that they spin and collide and create the sound of a triangle?
Well, it is fantastic that black holes that are just a few times to hundreds of times, 10 times the mass of the sun, something in that range, actually ring space-time in the human auditory range.
What?
Yeah, so the LIGO as an instrument
You told me
is
that once, and I said,
sensitive.
what are you talking about?
So LIGO as an
There's no
instrument
sound in space.
is sensitive to the range of the piano. So it's true, there's no sound in space because there's no air. And anyone who sees somebody screaming outside a spaceship is going to write complaints on Twitter that they don't know what they're talking about. But if you were near enough those two black holes, really near enough, your ear could technically ring in response to the gravitational waves.
What you're saying is your eardrum that is normally set into vibration by vibrating air molecules, in this case would be set to vibrate by vibrating fabric of space-time.
Yeah, it would pluck it like a string.
Yeah, like a harp string.
Yeah.
Ooh. Wow, that's weird.
That is weird. That's
I
pretty
don't.
wild.
Yeah, I know.
like
You
it.
could if you heard that, get out, move away. Imagine you would see nothing.
No, if you heard that,
You would see
it's
nothing.
too
but you
late.
It's right.
Right. Too bad it doesn't actually. Maybe that's what it says when you hear it. Instead of a
warning sign.
boom, it's just like a ha ha ha. You're cooked.
So what would hold my eardrums aside? What would my body feel if a wave went across my body?
So presumably right now there are black holes colliding all over the universe,
Right.
and we're being squeezed and stretched. But again, it's so weak that we don't even notice.
If it's strong,
If it's
will I say,
strong-
"Ooh, I felt that," or if it's reshaping the fabric of space and time, and I occupy that coordinate,
Yeah.
wouldn't I just shake with it and I wouldn't even know?
Yeah, probably most of these.
Get that, Chuck? What I was just saying?
Yeah.
If you're in,
You're
if I draw a stick man on a rubber sheet and I bend the rubber sheet, the stick
Yeah.
man goes with
with it.
Yeah.
Yeah, so I think
without
that's-
even knowing that he's being bent.
It's just this is my
Right.
how I'm doing it.
But the difference with the stick man is that we're bound together. So, for instance, your head is harder to squeeze and stretch than your eardrum.
Speak for yourself.
So, if you were, if you were there, your ear would start resonating more willingly than your head would. So, the fact that we're bound means we're resisting to some extent. So, the whole Earth, when the wave passes, doesn't really notice it. It's just so atomically bound to itself.
It would just be so funner
I think
if in fact we did.
Yeah, I think it's going to be more like for these long waves, it's going to be more like bobbing on an ocean, which is kind of what the mirrors in the LIGO instrument do. When the wave passes, they bob on the wave. It's not that the mirror itself is being squeezed and stretched. It's that it's starting to swing.
Okay.
And that's what you're looking for. You're looking for the motion of the mirror.
It's opened a whole new way of observing the universe. Is there any way to bring LIGO to bear on the Big Bang itself?
Definitely gravitational wave experiments, but probably not LIGO. So LIGO can put limits on the Big Bang. So the Big Bang might have actually made a bang. When the universe was created, gravitational waves were probably really cacophonous. It probably sounded like noise. But it's outside of really the range LIGO's optimally designed to detect. It's much more likely that a space-based instrument like LISA, the Laser Interferometer Space Antenna, if it ever launches, that LISA would be able to detect the sound of the bang.
So it'd be a cacophony.
Yeah, noise. Just like... Yeah. And so you asked me, how do you know it's black holes? Those two things sound really different.
Different.
Yeah. Black holes sound like... whoop. There's this...
That was good. Let me hear that again.
I don't know if I could do it again.
It's a black hole.
Called a chirp.
The black hole colliding.
That's a black hole colliding.
Those are two black holes colliding. Much less, I don't know, macho than most people expect. It has this sort of sweet little chirp.
Has anyone thought about how you get a 30 solar mass black hole?
That's a really excellent question. So not only was the first...
I don't know how you make one of those.
Right. And not only did they detect the first gravitational waves, but they actually started probing new astronomy. We had no idea there were black holes that big. The projections were for much smaller ones. And now we know there's 160 solar masses, so maybe there are 100
Maybe there's
or
some that are
150.
bigger than that.
Right. So did those already collide with other black holes to get that big? Or were they formed by direct collapse? Did they skip the Death Star state?
Right.
We don't really know. So that's already people are working on.
Yeah, because normally if you learn about black holes in your astrophysics class, what did you get in your
My astrophysics. I'm
Taking it with me next
much
semester.
Okay, excellent.
No, I got an incomplete. That was. I got an I. I got an I in astrophysics.
So we learned that one way to get a black hole is the end point of a high mass star.
Right.
Yeah.
But the high mass stars are 20, 30, 40, 50 solar mass, but they lose a lot of mass en route. So by the time it's done, you don't really have 30,
Much
40,
left.
50,
50,
60.
60 solar mass.
No.
But now we know for a fact that we do have one because we
Right.
watched them collide.
LIGO picked them
There
up.
are some people that think they're pure dark matter, that they don't form from stellar collapse, that they're not the death state of a star, that they're an
And I'll tell you,
example of
I'll
dark
tell you
matter.
this, just as a vote for science here, anytime we have a new instrument that takes us into a parameter space where we had not previously looked, you discover stuff that nobody ordered.
Right.
Now you can now a well-designed experiment is thought up to test for something that you have an idea about, right? So we think we will detect colliding black holes. You do it, and oh my gosh, it's a kind of black hole we never even thought was there. Right. And so good science is that which shows that maybe you're on the right track to begin with, but then opens up whole new places that you never even knew. So now the next generation LIGO is going to know how to tune it, how to be better at what it is for the new stuff.
And they'll discover 60 solar mass black holes that will collide and say, damn, look out.
Look,
That.
no, it wouldn't be.
That's where you're going.
No, Chuck, it wouldn't be the 60s because the 60s would be more powerful than the 30s.
Oh, right.
So it would detect lower mass black holes or the 30 mass black holes farther away.
Farther away.
Right?
Also, what about something we've never even thought of before? I mean, you think of the time Galileo first pointed the telescope at the sky, he's looking at Saturn, he's looking at the sun. He's not thinking quasars and black holes. Those things aren't even conceivable to him. And what we all really hope secretly is that we're going to discover stuff in gravitational waves that we couldn't possibly see in light. After all, 95% of the universe is completely dark. Right, exactly. So maybe there's something out there that we have not even thought of, and that is what everyone hopes for, to be honest.
Just think about that.
It's very cool, man.
Some crazy noise.
Yeah, because there's
Some
stuff
crazy
we
noise
had no
comes.
idea even existed
Yeah.
until we opened up new windows
Yeah.
of observation onto the universe. Right. Stuff that only talks to us in ultraviolet or in infrared. Until we had ultraviolet infrared telescope, it was not there. The birth call of the universe itself. The cosmic microwave background is microwaves.
Right.
Yeah.
That was a non-thing.
gotta see
we
them
had
in that.
microwave detectors.
Right.
Yeah.
Nobody even talking about
Yeah.
the early universe. So you could do that.
And now, thanks to them, we have Hot Pockets.
So can you give us just some final reflections on Einstein's life so that if we want to think, if we want to live, you know how a religious person would say, I want to live the way Jesus lived, right? So in the geek world, you say, I want to live the way Einstein lived.
Yeah.
Is there anything that you can tell us?
I really admired, above all else, Einstein's independence of mind and spirit. So when everyone else was saying, oh, there's something wrong with this supposition that the speed of light is a constant, that just makes no sense whatsoever.
Right.
Einstein,
Still doesn't really make sense.
it's really challenging. But Einstein accepts, and this is something that's often misunderstood in the idea of relativity, he accepts the rigidity of the constraint. That's what he does. And then around that constraint, he sees where he's free to move, and it's very limited. But from this tight constraint, he makes this, like, it's like squeezing a balloon in one direction and it blows out in the other direction. It's like it leads to things that were so much more magnificent than just allowing the speed of light to not be constant.
You know, it's interesting that you say that. I just thought of this now.
Yeah.
The worst thing you can tell an engineer is build this and there are no constraints and spend as much as you want.
Right.
It's like, oh my gosh, I don't know what to do.
Yeah.
But if you say it's got to be 30 kilos in weight, in mass, and it's got to use this much power, and it's got to fly in this way, and it's got to be made of these materials, go.
Right.
Then that's where the creativity.
Absolutely.
And so, for example, how do you get a telescope bigger than the width of your rocket into orbit? How do you do that? And people say, "Oh, okay." You tell the engineers.
Right.
They invent a telescope that
Unfurls.
unfurls.
Right.
Who ordered that?
Think of that.
Who would have thought of that?
Necessity is the mother of invention.
Think of it because I didn't let you do something else.
Yeah. I think this
And
is
I loved your reference to Einstein in that context. It didn't constrain him; it liberated him.
That's
So
right.
I want to ask you
exactly.
something because you just sparked a question in me.
Make it quick, 'cause we're running out of time.
Out of time? Okay, so you said about Einstein and light being a constant. So when LIGO detected the pulsar, the
that
neutron
called-
star.
oh, the neutron stars,
the
yeah.
neutron star.
Yeah.
When they detected that,
Yeah.
did they make the detection and see the light at the same
Yes,
time
and this
since the
is-
light is a constant?
This is why everyone was incredibly excited. It might be, at the end of the day, the most highly studied astronomical event in history. Basically, some huge fraction of the entire international astronomical community turned telescopes, satellites, all kinds of instruments in the direction of the collision.
We do that.
It was a
We're
network.
good about that.
Astrophysicists.
We good.
I mean,
We
just
good
like
that way.
No, I got your back.
We got your back. No, it's a very important thing.
amazing. It was
I'm in the middle of
thrilling.
my own research program,
Yeah.
and then in the old days it would have been a telegram. Now it's a, oh my gosh, there's an event over here.
Gotta drop it.
And I have my detector, which is different from your detector, different sound. Now we have 9,200 different kinds of detectors getting different
at one
aspects
event.
at one event.
Yeah.
And you look at this part, and I look at that part, and I look at this wavelength, and you look at that wavelength, and you put that all together. You all eyes, all hands on deck.
Yeah.
All telescopes, check it out.
It was really remarkable. So LIGO caught about a minute in the recording, but all of these telescopes combined caught, a month. Wow. And it kept spiking in different wavelengths. It would go in the infrared, in the gamma ray, in the X-ray, and so all these different instruments had their time.
Wow.
Yeah. So that's how we roll.
Collaboration, international collaboration.
Got each other's back, guys. We gotta shut it down here. But Chuck, always nice to have you.
Always a pleasure.
And it's even more nice to have you. We'll find some excuses to talk about Einstein and the universe
Love it.
just to get you back.
Love it.
All right. You've been watching and possibly only listening to Star Talk. I'm your host, Neil deGrasse Tyson, your personal astrophysicist. And as always, I bid you to keep looking up.